Welcome to the deep dive. Today we are taking on a true titan of thought, Alan Turing. Now, when you hear his name, you instantly think code breaker, right? The guy who beat Enigma.
Or maybe the father of computer science. That's the other big one.
Exactly. And those labels, they're correct, but I feel like they're also too small. They kind of trap his legacy in the 20th century.
They do.
We're going to argue that Turing's real disruptive insight was something far more fundamental. He figured out how to translate these incredibly mysterious processes.
Things like thinking itself.
Yeah, or biological form, how things get their shape. He translated them into precise, trackable, mechanical patterns of motion.
He basically just dissolved the boundary between abstract logic and, physical reality.
And to really get that, we need a special lens. We're going to filter Turing's work through what we're calling motion theory. The idea that motion isn't just what things do,
But what everything fundamentally is.
So before we jump into the machines, let's quickly set the stage with that filter.
Yeah, this is crucial because if you use the standard vocabulary, you just end up in these philosophical dead ends. So if we accept motion as primary, the first thing to go is the idea of a static object.
Okay.
When you think about a river or a flame, you can't point to one water molecule and say, that's the river.
Right, the river is the flow.
It's the continuous structured flow, the motion pattern. So in motion theory, an object, a galaxy, a rock, a computer, is just a long-lived, stable pattern of motion. It's held together by constraints.
That reframes everything. So, okay, if an object is just stable motion, what's time?
Time is just how we measure stable motion cycles. A clock is just a reliable, repeating motion pattern. The swing of a pendulum, an oscillating crystal. We use that pattern to track other, more complicated ones.
And what about a field, like gravity?
A field is just a motion gradient. It's a map of how motion prefers to flow. And our whole mission today is to show how Turing, just with logic and paper, basically discovered these principles himself.
Okay, let's start where he did then, with the very definition of rational thought. He asked this almost absurdly simple question. What is a single step of calculation?
Right.
And he wasn't thinking about, a circuit board. He was watching a person, a computer, that was the job title, sitting with a notepad doing that.
A human computer?
Yeah. And that person is performing a ritual. They look at a symbol, they remember a rule, they write a new symbol, and they move their focus.
And Turing stripped away all the biological messiness, the getting tired, the making mistakes.
And he boiled it down to 4 mechanical operations. The Turing machine, a simple reading head, a rule book, and this infinite tape of symbols.
And in our framework, what he did was translate reason into highly constrained, trackable motion. The computation is the motion of the head on the track, the motion of the symbols changing.
And the motion through the internal states in that rule book.
Exactly.
But hold on, if that's all reason is, just this head moving on a track, following a rigid rule book, doesn't that make it all, I don't know, a bit boring, a bit deterministic? Where's the creativity?
But that's where the power is. The local rules are simple, yes.
Yeah.
But the global behavior, the computation itself, is this incredibly complex, long, twisting path.
A path in what you call configuration space. That sounds a little dense. What does that actually mean?
Think of it like a giant map.
Yeah.
Every single possible state the machine could be in. So the symbol it's reading in its own internal state, that's one point on the map.
Okay.
As the machine computes, it moves from one point to the next. It's drawing a path. The complexity isn't in any one step. It's in the incredible length and, the sophistication of that path.
So a computation is literally the structured motion that gets the system from the problem to the answer. That path is the machine's mind in action.
You got it.
Which means information isn't some abstract thing. It's just how we label the difference between motion patterns.
Precisely. A bit is just this motion pattern or that motion pattern. And this is Turing's genius. A tiny set of local rules choreographs motion into these huge, globally meaningful structures. Nature does this all the time.
Like what?
Think of snowflakes. They lock into these perfect lattices just from local chemical bonds. Or how a fluid flows. It's solving complex equations without knowing any math. Turing gave us the simplest possible version of that principle.
Okay, so the Turing machine was revolutionary. But his next leap? That was world-defining. Universality.
The universal Turing machine. The UTM.
This is the moment computation really broke free of specific hardware, right?
It's the bridge from mechanical motion to simulation.
Yeah.
Turing proved you don't need 1,000 different physical machines for 1,000 different tasks. You just need one.
One structured motion system.
They can simulate the motion of any other structured motion system. You give the UTM the rulebook for machine A and its starting data, and the UTM will perfectly adopt the motion pattern of machine A.
So it's motion mimicking motion. That is a staggering concept. It's like having one single instrument, one physical box that can sound like a piano or a guitar or an entire orchestra.
That's a perfect analogy.
The instrument is the stable structure, and the sheet music is the temporary motion pattern it adopts.
Yes, the UTM shows that a rich enough motion pattern, the hardware, can stand in for any other possible motion pattern as long as you encode the instructions.
And this connects to some of the deepest questions, doesn't it? If the universe follows laws, then you could see the universe itself as a universal motion fabric.
Right. And galaxies, atoms, life.
Yeah.
They're just different, incredibly complex programs running on that fabric.
Turing basically built the toy model of the ultimate motion simulator.
He proved that motion can store its own rules and then use those rules to simulate the motion of anything else. It's this incredible closed loop of self-reference.
Okay, so that covers the motion of logic. But he didn't stop there. He then applied this exact same principle to the biological world. We need to shift gears to morphogenesis.
How patterns appear in nature.
He wasn't just thinking about computers anymore. He's looking at seashells, zebra stripes, the patterns on insects. How on earth did he bridge that gap from code to chemistry?
Because he saw the underlying story was identical. It's all just rule-driven motion. He came up with reaction diffusion systems, which create what we now call Turing patterns.
Okay, explain that.
Imagine you've got a simple chemical soup in some tissue. You have two molecules, an activator, which encourages a pattern to form.
And an inhibitor, which tries to smooth it out.
Exactly. And they both diffuse or move through the tissue, but, and this is key, at different speeds.
So this is a pure motion story, a tug of war between competing motions.
The tug of war is between diffusion, which is a smoothing motion trying to make everything uniform, and the chemical reaction itself, which is a sharpening motion that amplifies any little differences.
And what happens?
You start with uniformity, but some random fluctuation gets amplified by the activator. The motion freezes into a stable spatial rhythm. The activator makes a spot grow, but the fast-moving inhibitor races out and suppresses any other spots from forming too close.
Ah, so the distance between the stripes on a zebra is set by the relative speed of the motion of these two chemicals.
Exactly. The ratio of the diffusion rates choreographs the geometry. And this doesn't just explain leopard spots. It explains sand dunes, oscillating chemical clocks, all of it.
That is just astonishing. The same man who formalized how logical structure emerges from moving symbols on a tape also figured out how physical structure emerges from moving chemicals in a tissue.
He showed that emergence, whether it's logical or biological, isn't magic. It's a predictable result of simple, rule-driven motion.
Okay, so we've covered what motion can achieve. Let's pivot to his most profound discovery about what motion cannot achieve: the halting problem. This is where the dream of total predictability just hits a wall.
A hard logical wall.
The standard definition is simple enough. You can't write a program that can look at any other program and predict if it will ever stop or just run forever.
Right. No universal halt checker.
But when we translate that into motion theory, what does that actually mean for the physical world? Why should a non-halting program matter for, say, predicting the weather?
It matters because the halting problem proves that for certain classes of structured motion, there's no shortcut to knowing their fate.
No shortcut.
There is no universal way to look at an arbitrary motion rulebook, whether it's code for a CPU or the local rules for a turbulent fluid, and predict its long-term fate without just simulating the motion step by step.
It's computationally irreducible.
Exactly. The only way to know what happens is to let the motion unfold. You can't compress it.
That feels like a massive limitation. I mean, the goal of science, especially physics, has always been to compress reality into short, elegant laws. Newton's equations compress a planet's orbit.
Precisely. A planet's orbit is computable motion. We can write a short recipe, plug in the start conditions, and know where it'll be in a million years. It's compressible.
But the halting problem guarantees some things aren't.
Right. Think about water turbulence, or an ecosystem, or even a really complex pinball machine. The motion is so interlinked, so dependent on every tiny fluctuation, that the only recipe for its future is the motion itself. You just have to run the simulation, or in the real world, just watch it happen.
So when we look at messy things, climate models, biology, fluid dynamics, Turing is telling us they might be fundamentally uncompressible. It's not that we aren't smart enough to find the equation.
It's that no perfect short equation might exist in principle. The complexity isn't a temporary bug in our understanding. It's an inherent feature of the motion pattern itself. It forces us to accept a whole spectrum of predictability.
Okay, that leads us right to the ultimate question of intelligence, the Turing test. If the difference between reason and biological form is just structured motion, what does that mean for the mind?
Well, the test is brilliant because it's purely functional. It just asks, can one structured motion system, the machine, replicate the output motion pattern of another, the human brain?
In the context of a conversation.
Right. It totally sidesteps all the philosophical baggage about consciousness or soul. It just asks, is the machine's motion pattern effective at playing the role of a thinking human?
But some people would say that reduces thought and creativity to just a mechanical sequence of inputs and outputs. It feels cold.
Or it gives us a framework for what mind actually does. Mind isn't some ghost. It's a class of incredibly effective structured motion patterns that emerge through evolution to help us survive.
What does that motion pattern do?
It compresses incoming streams of environmental motion, what we call sensory data. It creates internal models of reality. It predicts future motion. It plans actions. If a machine's motion pattern can do those things, the test suggests it has achieved functional equivalence. The universe doesn't care if it's neurons or silicon getting the job done.
So that brings us to the final synthesis. If we put the halting problem, universality, and Turing patterns all together, we get three really profound lessons about reality. First, motion can store and transform its own description. The universal machine is motion modeling motion. The brain does the same thing. That's a huge evolutionary leap.
A major loop gets closed there.
Second, not all motion is compressible. The halting problem shows that while some things are simple, much of reality complexity, maybe consciousness is irreducible, the recipe is as long as the thing itself.
No shortcuts.
And finally, emergence is rule-driven motion, not magic. Turing patterns prove that complex structure, whether logical or physical, arises naturally from simple, local rules. It's the template for everything from a cell to a mind.
I think Turing's true legacy isn't just the computer. It's his unified vision of reality. He showed us how to write motion as code, how to let motion simulate motion, and exactly where that dream of total compression breaks down.
He showed that thought, pattern, and form are all just different ways motion can organize itself.
That's it, under constraints.
Thank you for joining us on this deep dive into Alan Turing and the mechanics of thought.
And here a final provocative thought for you to explore. If the universe is a single, continuous motion fabric, and the halting problem proves that its long-term fate is often irreducible, meaning the only way to know what happens next is to let it happen, does this suggest that reality is constantly surprising even itself, moment by moment?